Alright, so today we're going to be doing day 15 in Advent of Code. Today's challenge, part 1, is going to be that we're going to get a grid in the input file and we're going to get some amount of moves that we're going to do. So if you imagine that the @ symbol is a robot, then the robot does exactly these moves. It goes left first, then it goes down, then it goes down again, it goes right, up, left, down, and so on and so forth until it finishes the entire sequence. So if we imagine that it is right here, the dots are empty spaces, so if we move up, we can do that directly, there's no problem. The circles represent a box. If we go left, what we have to do is to just push the box over. So the O will end up here and the @ will end up here. And the hashtag signifies a wall, so we cannot cross it no matter what. Even if the @ was here and we try to go to the left, then nothing will happen. We just don't move because we can't. And we go to the next move that they asked us to do. And there are some examples here, and let's see. So over here there's two boxes and we're trying to move right, so both of them will move to the right, as you can see. And if we move down here, I don't know if they eventually do that, they do, then we can see that all of these four boxes move down together. But what we have to do is to check sort of recursively, okay, is there a new box, is there another box, is there another box, and then if there is a free space at the end, then we know that we can move this entire sequence. And move the @ symbol itself. So we can keep doing new moves. So if you look at the input file, our actual grid is a lot bigger than the sample that they've given us. And we can see that the @ symbol is somewhere in the middle. So presumably there's going to be a lot of different moves in all sorts of directions. And we can see how many moves there are. There's a lot of different lines as well, but that's just to make it easier to see. But we have to read all of these lines. And first thing we have to do is to parse the information. So we can go ahead and get started with that, and we can see that the information when it comes to the grid, it always starts with a hashtag. So you can either split it by wherever you see two new line characters, and then you know you're gonna get the map first and then the coordinates or where to go step by step after. Or you can just see, okay, wherever there's hashtags, that's part of the map, and after that, then it's no longer part of the map. So that's what I've done here. Firstly, you read the entire file, and I put it in lines, and then I go for each line. I look, okay, if there's a hashtag in the line, we don't see any hashtags in the instructions, so then it's great. So there's a hashtag in the line. We can also check line 0. That works as well because it's just the first element. Then we remove the \n because it's at the end here and we don't want it. And I add each character to a grid. So I've made a final grid here, and I've made it filled with dots. So there's 50 dots, and then we make a for loop, for underscore, so we don't need to give a name to this. But we just want to iterate over the range of how many lines 0. So the 0th index, so this entire thing, so how tall it is, should be how much it iterates over. Or no, lines 0, right? Line is just this one line, and then, no, yeah. Line 0 should be this entire length. So from 1 to 50 is 50, but yeah, the reason that it doesn't really matter if you put lines 0 here or 50 here is because they're both actually 50. I'm not gonna sit here and count if it's a 50 by 50 grid, but it looks like it is like that. But we want to make a for loop, because if we just say, okay, to make two different grids and then multiply by 50, then it's going to copy the exact same grid. So it's going to use the same address in memory, and when we update one of the rows, all of the rows are going to update with that amount. So what we want to do is to do this instead, a for loop, to create the grid, to be able to have each separate row be distinct from each other. So once we've made the grid, and we've also made all of the moves, which I've also removed the \n characters, and then I've added every move to the moves list. I've printed it so we can just see how it looks, and it looks about right. There's all the moves over here, which is a lot of them, and then we have the grid, which doesn't look great because it's not a perfect size over here. But what we can do after this is we can go through all of the moves, and we can find the coordinates where the robot begins. So if we just search here for the @ symbol, then we see it begins here, but we need to find it in the program, and it begins somewhere. So what I do is I just iterate through the, not X and Y coordinates, but through the rows and columns, and then wherever I find the @ symbol, I just return the X and Y coordinates. And I use this a lot actually. Every time that we move the robot, I could keep the coordinate of where the robot moved to, and then just keep going from there, but I just implemented it like this. I know it's less efficient, but it was a long day, okay? So we do that, we get the new robot coordinates, and then we check, is the move that we're going to do left, right, up, or down? And whatever direction it's going to be in, we're gonna send it to move to, which is gonna get the coordinates of wherever the robot is now. And then I send it the rows and columns in some numbers, and then the final grid, of course. So what this means is if we're going to the left, then the rows will not be moving, they will be staying the same, but the columns will go -1, so that means left. If we go into the right, then the columns will be going to the right, but the rows will be staying the same. If we're going upwards, then the columns will be going -1 index, meaning if we're at 4, we're going to be at 3, which is above. And then when we're going down, we're going to be adding 1 to the row to the row index, so it's going to go from 4 to 5, so we're going to go down. So this function here is going to actually move us and check if there's obstacles and if there's boxes, and to be sure to move all the boxes. So first thing that we do is we check, okay, is there no obstacles? Then great, just move the robot, remove it from where it was and add it to the new place. So that's straightforward, and then we just return true, we are done. But if there's a box, what we have to do is we have to keep the original box. So if we see the @ symbol over here, we see there's a box, 3 boxes below actually at the starting position. So if we try to look down, if we found a box, we have to keep looking in this direction until we find either an empty space or a hashtag. So empty space means that, okay, we can move all of the boxes that we've just seen. If we see a hashtag, it just means, okay, cancel everything, we can't move, do your next move instead. So that's why I've done the while true. And we check again what direction it's going in. I could have sent it a direction that it's going in, but it doesn't take that long to check the direction right now. And what we do is we just keep adding to the same direction that we're going in. So if the go row is above 0, then it means that it's going positively in the row direction. So we just keep adding 1 to that. So whatever direction we're going in, we're gonna keep going in that direction. And we're gonna see if we found in the new place where we're looking, if we found a hashtag, then it means that we can't move it. But if we found a dot at some point, then it means that we can move it. And what we have to do is we can, this is for part 2, don't mind it. So if we have the @ symbol here, and then we have a bunch of zeros, and then we have a dot here, what we can do is we can just take the first one and put it here, and then it will become 0, 0, 0, and then, well, it will still be the 0 here because we're technically just copying it. But then the @ symbol, we can put it here, so this will become a @ symbol. Pretend that's a @ symbol, and then we delete the @ symbol here, so just making it into a dot. So that's what I've done here. That's why we only need the if statement and to change a couple things back and forth, because we're only moving the O to the last place and then the @ here, and then we're deleting the @ where it was originally at. And this is good because these are not like specific values that we need to keep track, so we don't need to actually move them. We just need to represent that they've moved. And this works for part 1, great. So if all of this worked, then it's going to return true. and I don't do anything with true or false actually, but it's just good to know that it worked or not. So finding the box coordinates are here, and then once we've ran through the entire moves, we're going to call box points, and let's see where I call it. So once we've gone through all of the moves and I printed the grid and the moves, we see we calculate the points, and the way that they want us to answer is we have this is the result, for example, and then if we have this box over here at, let's see, 1, 2 away from the left side, then we add 2 points, and then if it's 1 away from the top side, we add 1 point times 100. So top down, we have to multiply by 100. That's how they want us to do it. So that's what I've done. I've gotten the row and the column. So we take whatever row it's at times 100 and then plus the column, and that's, they want us to add that to the total, and we check that for every box. So that's why I iterate over every row and column to be able to find every single box that we find, and then add it to the total, and then we should get an answer. So it's 1,500,000 something. So if I run it, and it takes a second, it just printed the last thing here, but now we can see that it also printed the box points, 1,500,000 something, and then 863 at the end, which seems to be correct. So that was part 1, and now for part 2, what they want us to do is to sort of duplicate how big the entire map is. So that's one part of the puzzle. They want us to make the map twice as big. Why? Because now the boxes, instead of being represented as O's, they're being represented as these brackets, and it's going to be interesting later. And then the @ symbol is just going to be on the left side of wherever it was, so not both of these will be the @ symbols, it's just one of them. So now the thing is that if these are boxes, if we move them up or down, well, right now nothing is special, but the thing is when we move it left or right, we're gonna have to keep in mind, okay, we have to move both of these, and then this symbol has to end up here and this symbol has to end up here. We can't just scooch this one to the end. And then if we only move it one step, so yeah, there's an example here, then we get sort of like a triangle shape. So if the @ symbol ends up under here and then pushes up, then we have to check, okay, is this box sort of in the way of this other box? Then it means that it will push all of these 3 boxes. So we can see the @ symbol goes under here and then it pushes everything up. And if it tries to move everything up again, it sees that there is a hashtag here. So this box is being blocked by a wall, so it can't keep going up. So every top side of the box has to be free to be able to move it up again. And this is for moving up, and then there's also moving down, left and right. So we can kind of imagine that moving left and right is the same as moving half in the original one. But the first thing that we can do is make the new grid. So I have the original grid here, and then I've made a temporary grid just for now, and then I iterate through the old grid. So wherever I find a hashtag, in the new grid I add 2 hashtags. Wherever I find a O, I add a opening bracket and a closing bracket. And you can see that I add it at the same row, but only the column becomes twice as large. So I add it at 2 times column minus 1, meaning that it's going to be on the left side, and then on the right side of where that index would be is going to be the second part. So I do this for every single symbol. For the @ we leave it on the left side, that is why it's at the -1. And this is how we construct the new grid, and then I just reassign it to the original grid. And the reason that I made a temporary one is because, well, I have to know what's in the original one to be able to place them to the new ones, and it would just be more hassle to place it in the same one while I'm updating it. So now that we have that, we do the exact same thing again, 4 move-in moves, and we get the robot coordinates again. We move to the special coordinates, and what we do now is we don't only check, okay, is there a free space? Okay, just move the @ symbol and then If there's a circle, then do something special. We have to check for each direction that we're going in. So if there's a box, then we have to know where we're approaching it from and what to do with it. So if we're going from the left, I check, okay, the go row should be 0, and then the go column should be -1. That's how we know that we're going to left. And then if we're going to the left, the box should look like this always, because from the left side, if we look to the left, that's the box closing from that side. So if we find this symbol, if there is a box there, then I want to keep iterating. So the same as we did before with keep finding all the O's, but I want to keep finding all of the boxes until I find a free space. Once I find a free space, what we do is, instead of scooching them one by one, we have to move them from the last place. We move them one, and then this one moves here, and then the @ symbol finally moves into this place. So we have to move them one by one in this case. And we only do that once we found a dot, so we know that there's a space if there's a dot here, or once we found a hashtag here, which means that we cannot perform the movement, and then we just return false. So that was going left, and I could have made the going right into the same if statement, but I've just written it again. But instead it's with the open box, and it's a bit different with the indexes when we replace the @ symbol and everything. So that's for going left and right, and that's pretty straightforward. We just have to move the different stuff. But now when going up or down, it gets a bit more complicated, because you can sort of stack them. So if you have a box here, and then you have another box here, and then another one here, so we have to sort of recursively look, okay, is this if we're right here at this @ symbol, we have to look above us. Is this a box, part of a box? If it is, we have to find its pair, so its soulmate, as I call it. And both of these places have to check upwards as well. Is there a new box? If there's a new box, find its soulmate as well. Find this one, find this one. So we have to recursively check and find all of the boxes. And then once we've done that, if the above is dot, 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 and then hashtag here, everything was valid until we found this hashtag here. So we cannot move any of these because there's a wall here. And we do that in this function, and it checks if it's up or down. And we can collect the boxes and validate it directly by giving it the final grid, the next row, next column, and so on. And here's the function. So we find all of the boxes by using a BFS style search. And I keep adding to a specific queue. So if we find a soulmate, so the other side of the box, then we add it to the queue, and we want to also search through it for other boxes. And also I want to check for more boxes in the same direction of movement. And if there is at any point a wall, then we just want to return none. So we don't want to return any boxes, because once we go in this function, where is it? Once it returns here, if there's nothing, then it just returns false. So it knows that we did not find a valid sequence of boxes with valid amount of empty spaces. So it was just a bit of a pain to set up and to make sure that the statement works, and it was a lot of debugging. And I can debug it really quick to show how it moves sort of step by step. But let me just put this to sample so it's not crazy big. I have the sample file as well in here. Oh, not run normally, run with debug. Yes, start another instance, and let's hope it doesn't take too long to start running. But we do get the correct answers, just that we have to check for left, right, up and down, and then there's so many different cases that can happen, and different things you have to check. So I'm gonna take this away for now, and we can see that we have the final grid here. And over here, I stopped it at if you click here, you can make a stop breakpoint, and if you right click it, you can edit the breakpoint and make it into a hit count, and you can put it to whatever you want. So I've set this one to like 253, I think, and that's exactly when this one tries to go down, and it tries to push this down. So we have to recursively look at this. Okay, this one is touching this one over, oh no, this one over here is touching this one, and then this one has this soulmate, but this soulmate has free. Okay, but just because these two have free, and this doesn't mean that we can go ahead and move. We have to check this one's children, if you want to call it that, and then this one's, and we can see that we finally hit a wall. So actually we can't move this down. It kept giving me the wrong answer, so I had to go step by step and see, okay, where does it go wrong and what instance does it go wrong. So I saw that when it was trying to move down here, for some reason it was not iterating through all of the different children that it found, different boxes that it found, and it was just saying, okay, go ahead, here's a free space, there is space, just move this down, and then it was a catastrophe. But now it actually checks it correctly. So if we go one more step into here, then yeah, it did not go down and it just went left, which was the next step. So it works as it should. And what else? These are for the up and down directions, and we have the find the soulmate function, which is just if it's an open bracket, then we know that it's just gonna be on the column +1. If it's a closing bracket, it's column -1. I could have just said that directly, but I found it a bit nicer to implement this function. And then we also have this function to check what's above or below. So I just give it certain coordinates and what direction we're going. And then we're looking, okay, did we find a box, a wall, or is it free? And we use this function inside the... Never mind. It looks like I completely removed the functionality of this function. But I've used it before I updated the... Whoops. Before I updated the code. So if we run this right now, we should get not 9,021, but a couple million, I think. And if we run it without the sample input, it will take a second and it will tell us exactly how many box points we have. And we also calculate the box points in the same way, but now since there's a lot more what's it called, columns and rows, yeah, a lot more columns, then the point should be a bit bigger. So it's 1,500,000 something something, and that was the answer, and it was correct. So now for the time complexity of part 1, what we have is the total number of moves that we have to do, that we also get from the input file, which is on the bottom here. And we also have the size of the grid, so we can get different size grids and we can get different amount of moves to do to the robot. So we have to keep in mind both of these variables when thinking about time and space complexity. But in conclusion, for every move that we have to multiply it by the size of the grid. So that is the complexity, because if there's a lot of boxes and we have to check a lot of different spaces, then in the worst case it will be n times m, and it's going to be the same for space complexity. And for part 2, it's quite similar. The only different thing is that now we also have k, which is the number of boxes connected during a traversal, and I've included this since it seems that it's quite common, and you should always think about the worst case scenario. So it's almost n times m, which is the same as part 1, but we also add k over here because we have to check more spaces, and it recursively looks into how many boxes are sort of attached together and then if they can move together. And we have the same story for the space complexity, that we have to add k to it because we're storing all of the boxes that are connected together into a different list. So that was the time and space complexity of day 15. And if you guys want to join the leaderboard, I'll leave the code in the description. And thank you for watching. I completely forgot to even put this on. And see you tomorrow, and happy holidays.